lead planning engineer at ERCOT, Resource Adequacy Group, primarily working on the system flexibility, frequency control, and performance issues related to high penetration levels of inverter-based generation. Her other interests are integration of storage and distributed generation. Julia serves as a number of technical advisory committees for projects related to high penetration of inverter-based generations carried out by NREL, EPRI, NERC, and others. Julia is chair of high penetration of inverter-based resources task force at Energy System and Integration Working Group, ASIC working group, and vice chair of NERC Inverter-based Resource Performance Working Group. Julia received her BSc from Riga Technical University in Latvia and her MSc and PhD from KTH. Prior to joining ERCOT, she was with consulting firms Parsons, Brinkerhoff, and Sinclair Knight Merge, working primarily on system planning studies, grid integration, and grid code compliance studies for wind power plants around the world. We are very happy to have you, Julia. We are very happy to have you here to present us, and you are going to talk about inverter-based resource integration in ERCOT, and the screen is yours.
All right, thank you very much for a nice introduction. I'm thinking when you're saying Julia is a common name in power systems, that means that programming software that you can use, programming language, right?
I mean, you are a recognized face in the circuit. I will be very surprised if our audience needed your introduction. But
thank you. I'm trying to share my screen. I'm not sure if you can see it.
I can see a camping site. Very nice.
Oh, so that's the wrong screen I'm sharing then. Give a second. I'll try a different one. Yeah, that's the one. All right. Camping site is good, but we need to talk about ERCOT and other things. Yes. All right. I'll put it in full screen. And, all right, so I'm assuming you can see it now in the right way.
It's perfect.
All right. So I'll go straight to business and first of all introduce Texas system. So ERCOT is independent system operator. So we don't own anything, no generation, no wires. We're just system operator and market operator, and we cover about 90% of Texas load and 75% of Texas land. Our peak load is about 75 gigawatt. We peak in summer because of air conditioning load. It gets hot here in summer, and winter load is less than that. It doesn't get cold here. We have more than 700 generating units. Most importantly, I think to mention is that Texas is large. We are about size of France, a little bit bigger than France. Population is about half of France, though, so it's sparsely populated, but big land. And we are not synchronously interconnected with the rest of the United States. So we have foreign HVDC ties, but even those ties, they are relatively small. It's about 1 gigawatt. You can see that comparing to our peak load, it's pretty small. So for everything, every service, frequency control, for balancing, we need to rely on the Texas system. We cannot rely on our neighbors because we don't have sufficient interconnection. And that makes operation of the system fairly interesting. So this slide has a lot of facts about ERCOT, and you can look at it later. The only thing here that I wanted to point out, we are still, let me see if I can grab a pointer at this point here. Yeah, so we have, we're about half natural gas based in terms of installed capacity. So we have combined cycle plants and combustion turbines. We have almost 25% in terms of installed capacity of wind. Coal is going down in size, so we have seen a lot of coal retirements lately. We have 5% of nuclear, so these are 4 large nuclear units in 2 power plants. Solar is just picking up, and you'll see more details on that. And we have a little bit of storage and a little bit of small generation of other types. So this chart is showing installed capacity of wind and solar that we have. So this darker color for blue and yellow is showing installed capacity for wind and solar all over time. And then lighter colors are showing what we have planned and for a given year. So if you're looking at 2021, we have 4.7 gigawatts of solar planned, and this dark purple color is showing storage that we have installed already, and light purple color is showing what storage we have planned. So as you can see, as of April 2020, we had about 31.5 gigawatts of wind. We have 7 gigawatts of solar, and we have about 500 megawatt of storage. And we have, more is coming up. So in 2 years, that number is supposed to grow like 1.5 times. So we're still installing more wind and more solar. So what you can see from here is that initially it was only wind, and solar started picking up slowly. And now, if you look at interconnection queue and what's planned, we have more solar coming up than wind. And this saturation is mainly because of, first of all, I guess like good wind sites are already, used up to an extent where good wind potential is in areas where transmission capacity is limited. And so solar becomes more attractive because it can be built in areas that are, closer to transmission and have more access to transmission. And I think it's also cost of technology that's driving it as well. But so overall, we are seeing more solar developments than wind in the interconnection queue. Also, one thing to mention, we reached instantaneous penetration level that's 66.5%. So 66.5% almost was served, of load was served by wind generation in March this year. Why I know it's just wind, it's because it happened in the middle of the night. Our patterns for wind are such that wind peaks at night in spring and autumn time. And so to kind of, we see less wind in summer during daytime when load is peaking. We still see some, but it's not as high as during shoulder seasons at nighttime. Something else I wanted to mention on this slide as well, that we don't have any renewable goals as opposed to other countries and even some states. They have renewable goals and mandates and things like that. We had that defined for 2015. Before we reached 2015, we already installed more wind than that goal was, and primary driver behind wind and solar developments in ERCOT is production tax credit for wind and investment tax credit for solar. So right now, this is what's driving it, but in the future, they will be building just purely economically. I just wanted to mention briefly, I don't have much information about it here, but I wanted to mention how we do forecasting. We started wind forecasting, I believe, in 2009. This is kind of showing structure of how wind forecasts are being created. So we create hourly forecasts that span 168 hours ahead, and we update those forecasts every hour. And then there is also recently been integrated a short-term forecast that's updated every 5 minutes, and it spans 2 hours ahead. And I'll mention why we have 2 forecasts. we use two vendors, so we can choose between two vendor forecasting. This slide right now is showing just for one vendor that we had before. And so what's happening every hour before the forecast is created, wind plants are sending information to our forecast vendor, and that information contains meteorological data from the site and any D rates that they have at the plant. So say if turbine is on outage, they will inform the forecast vendor so that they can put it into forecast. And then ERCOT also sends information sends this information to forecast vendor, and forecast vendor creates the forecast. And then ERCOT is using this forecast to make operating decisions in unit commitment and dispatch. And this forecast is also being sent to wind plant operators, because wind plant operators can choose to offer on the market something lower than what wind forecast is saying for them. They cannot go higher than that, but they can offer less if they feel like, there may be more D rates that happen in the meantime, or they want to somehow be on the safe side and offer less. They can set their maximum level at lower value. And then, I mentioned short-term forecasts. So that one we need for our real-time market. We run real-time market every 5 minutes, and previously we used to use persistence forecasts. So we'll just look at what wind is doing at the 5 minute when we run our real-time security constrained economic dispatch, and we'll say, well, wind will continue this way for the next 5 minutes, but we noticed there can be forecasts that are introduced with that. And now we're using this 5 minute forecast for real-time market instead. And then for solar, we only recently, maybe about 2 years ago, we started doing solar forecasting. Until now, we only had this longer term forecast, so hourly forecast with 168 hour time frame. But recently, we also introduced short-term forecasting, and it's going into our real-time market dispatch. This is just showing progression of accuracy for 1 hour ahead forecast error. And so you can see that with time, our forecast is becoming more accurate. We are working very closely with our forecast vendor and trying to improve forecasts continuously. So I mentioned in the beginning a little bit about our geography. So Texas is big, and Texas is also long. So if you look at, corner to corner, Texas is 1,300 kilometers. And what I wanted to mention that areas that are rich in wind resource are over here, this Texas Panhandle, it's called, and I'll talk a lot about this area today. So just wanted to point that out. And then also West Texas is rich on wind, and solar is being built there. There is a map from NREL that I don't have on slides here, but if you look at it, it's a radiance map. The highest irradiance for solar potential is in this area for Texas. However, if you look at this map, the biggest cities in Texas are all on this side. So this results in long distance transmission from areas rich in renewables to load centers. And that has its own set of challenges that I'll talk about much more. So this is all I wanted to point out on the slide. I'll talk next about two kind of big groups of challenges, and one is being weak grid instability, and then the other one being inertia and frequency control. I intentionally have an order this way because in our area, weak grid instability issues are much more pressing than inertia and frequency. And this is two parts because of some measures we already implemented in place to address frequency, but also because of characteristics of our system. So I already mentioned this Texas Panhandle area. We have about currently close to 5 gigawatts of inverter-based resources in this area. And we have more planned in the nearby area. So this area is already restricted in terms of transmission. So more generation is building right outside of the constraint. This area you can say that doesn't have any local load, and it has few synchronous generators there, but whenever wind is high, it's not economic for them to operate, so they turn offline. And so this area is basically 100% inverter-based area. And with that, there are stability challenges associated with weak grid conditions. And so what it basically means is you're trying to control voltage in this area. Inverters are, fighting each other because they are all controlling voltage in kind of a fast manner. And that resulted in voltage oscillations. This is measurement from actual event in 2012. And so after we recognized this issue, there were a number of measures taking place. So now only wind turbines with WinGrid control features are allowed to be installed in this area. We are also monitoring what's called weighted short circuit ratio, and I'll talk more about that. We do EMT, electromagnetic transient studies for this area to see how much can be exported outside of this area. And we do dynamic stability assessment for this area very carefully because that's the area of concern. And I have more details on this one. Oh, maybe one thing I wanted to mention. So this, what I have on this slide, that's what we had to date almost. And very recently, we, another area interconnected into ERCOT. So it's the city of Lubbock. It's right outside, it's in this nearby Panhandle territory somewhere here. And so that city used to be in a different interconnection, so it wasn't part of ERCOT interconnection, and recently interconnected into ERCOT. And so it brought about 500 megawatt of load. So that's substantial load for Panhandle, considering it didn't have any. And it brought two small synchronous generators with combined capacity about 120 megawatts. So that area improved a lot because of this interconnection of Lubbock, and some of the measures that I'll be talking about, they are not in place anymore because of this. But I thought it was still interesting to mention those. So in 2014, we did a Panhandle study, and we recognized it wasn't PSCAD, so it was regular study that we do, and it recognized limitations of this area and that this area is being weak. Before that, we used this short circuit ratio rule of thumb. So saying if short circuit ratio in the interconnection point is a certain value, then the grid is weak and you cannot interconnect there. But we recognize that the single bus short circuit ratio ignores interconnection to the neighboring inverter-based resources in the region. And so it may have overly optimistic estimation of system strengths for a given bus. And so since then, for Panhandle area specifically, we proposed this weighted short circuit ratio. It basically treats the entire Panhandle area as one bus, and it recognizes that there are other inverter-based resources in the area, not just one that you are looking at during interconnection process. And so it assumes that they are all interacting, and we proposed 1.5 as a minimum pre-contingency system strengths for Panhandle. Initially, it was based on PSCAD studies, as I mentioned. So currently, sorry, I just see if I have. I'll just mention it here. We actually also verified this 1.5 short circuit ratio in electromagnetic transient studies. We found that at different conditions below 1.5 ratio, the system can be operated stably, but you need to be changing this limit based on system configuration at any given time. So because this became kind of impractical in real time, we set the limit at 1.5, and it's been maintained in Panhandle and inverter-based resources. So it's mainly wind in this area. They are being curtailed as long as we see that weighted short circuit ratio is less than 1.5. We built in this calculation into voltage stability assessment tool that we run to determine steady state voltage stability. And we run this tool every 10 minutes. So apart from determining voltage stability limits, it's also calculating this weighted short circuit ratio. And if it is less than 1.5, it will curtail wind generation in the area. And so the limit is determined based on whichever is less. So its voltage stability is limiting at the time. It will set voltage stability as a limit. If weighted short circuit ratio is a limit, then that one will determine transfer limit outside of Panhandle. And all generation will be curtailed accordingly. When it calculates this limit, it of course considers current network topology and wind conditions and all of that kind of more real-time data. So this just showing real-time transmission limit, as I mentioned, either due to voltage stability or weighted short circuit ratio, whatever happened to be less at the time. And you can see that it varies over time. It is an advantage of doing it in real time because it allows us operating more flexibly instead of setting a limit very low and then curtailing wind more than it should. To improve voltage stability in Panhandle area, we installed 2 synchronous condensers, and you can see the characteristics here. They were placed in locations to increase weighted short circuit ratio, but also just improve voltage support and transient response. So it was kind of optimized location from different perspectives. And we went for high availability design for synchronous condenser. And this is because once the synchronous condenser is out, the transfer limit from Panhandle is going lower. And so it affects a lot of generation resources. And so we consider it that synchronous condenser needs to be fairly reliable and available. And so here you can see, so once we added synchronous condenser, export limit could be increased by about 470 megawatt. You can see this blue line. This is 2018, and when synchronous condenser was added, you can see that transfer limit is going up. But you know what happened when we added synchronous condenser is that we now had a situation where we have 2 relatively small synchronous generators. I mean, synchronous condenser, but it's a synchronous machine far away from the rest of the synchronous generation. So as I mentioned in the Texas map, Texas Panhandle is, you know, in the upper corner of the map, and then all large synchronous generators are on the central to east side of the system. And so there is long power transfer between these 2 parts, and having synchronous machines there resulted in this kind of classical inter-area oscillation during certain wind conditions, during certain system operation conditions. So when export was high from Panhandle and we transfer a lot along these long transmission lines, after a contingency, we see oscillations between synchronous condensers in Panhandle and the rest of the grid. So basically solving one problem of weak grid, introducing synchronous condensers, introduced another problem of these power oscillations. What could have been done in advance should we, you know, thought about this problem? Probably there are synchronous condensers that are equipped with power system stabilizers. So that what regular synchronous generator would normally have. And our synchronous condensers are not equipped with that. I'm aware of synchronous condensers installed in Australia, and they have a flywheel for inertia, and they have a power system stabilizer to avoid this oscillations. And so, yeah, as of today, we kind of just monitoring these conditions, and we can limit transfer from Panhandle to avoid this situation. It never happened in reality. We just seen it in studies. One interesting point to mention is that we try to get power system oscillation damping on existing inverter-based resources. So we kind of try to go out and require it, saying that all synchronous generators are equipped with power system stabilizers, and we are aware that inverter-based resources are able to provide power oscillation damping. But in the stakeholder process, we got a lot of pushback saying that this is not, you know, fully tested product, not commercially available. It requires a lot of testing and customized design for a given system and system conditions to work properly. So, I mean, more work is needed to have this feature. So this slide is just showing a lot of text here. I won't go through everything, but it's showing we're seeing increasing number of stability related constraints. So the Panhandle is just one that I mentioned, but we're seeing more and more where transmission cannot be utilized to its thermal rating because of stability constraints. And this is again because inverter-based resources are being built on the edges of the system. So you can see it's here, and in these areas, these are areas where we're having new stability-related constraints. And so stability constraints, they need to be assessed in the offline studies, and then we need to implement them in our real-time market because we need to dispatch around those constraints in real time. And these constraints, they're not necessarily on just one line, they may be on corridors like Panhandle is. So they're relatively complex. It's not only about defining constraint itself, but it's also about defining limit on this constraint, and limit will vary in time. So we fix constraint based on our offline studies, planning studies, but then closer to real time, based on topology at the time, we use offline static tables to determine what constraint is at any given time, okay, what the limit is on the constraint at any given time. And you can see we are seeing increasing number of these constraints. In 2020, we had 15 of those. And so they're becoming hard to manage, and they complicate our real-time economic dispatch as well. So this is just showing kind of the result of these constraints. It's of course results in curtailments. So what you can see here is installed and synchronized capacity of wind and solar at any year, and then percentage of wind energy that was curtailed in that year in blue, and in yellow this is solar curtailments. So you can see, I mean, in some years it's going down because of some transmission reinforcements that have been made. But overall trend is all going up, and this is because we have all these generic transmission constraints related to stability that cause curtailments. We use a number of stability assessment tools. I already mentioned EMT studies. So initially, the first study was done by a consultant for us, but then we realized we need to do these studies. And since maybe 2016, we've been doing PSCAD studies every year. So PSCAD study is done for Panhandle, and then maybe since 2018 we also include South Texas. So this is area at the bottom. It also has kind of long transmission to big load centers, and so this area is also of concern because of weak grid. In those studies we check if this weighted short circuit ratio of 1.5 is still applicable, or if something else needs to be used. And then we use PSCAD for other studies, for like all actual stability studies. And we use, as I mentioned, VSAT, voltage stability assessment tool in real time to assess steady state voltage stability for long distance high power transfer. Here you can see stability issues that we are kind of scanning for, and I talked about that. And here there are tools and operations that these studies in planning kind of fitting. I already mentioned weighted short circuit ratio that we determine from PSCAD studies, and then we keep it in real time. We calculate in real time based on actual conditions, keep it below 1.5. We have offline tables for stability constraints, and so for a given configuration with given planned outages, it will look at what constraint on a given stability, what limit should be set on a given stability constraint. Now, we're currently developing a transient stability assessment tool in real time. So, I mean, the tool exists. We are trying to deploy it in real time so that we can assess transient stability in real time as well, instead of setting limits based on offline studies. That would be very advantageous because it will allow us to operate more flexibly and allow more export from some areas where there are stability concerns. The hold up with this is because it's a different tool. So we used PSSC before and we used PSCAD before, and we require models for inverter-based resources in both of these tools already for some time. Whereas TSAT is a new tool, and some vendors, they need to develop models for TSAT, and that takes time. And it's not only model development, but it's also model verification. We need to make sure that all three tools that we are using provide are yielding consistent results. So this a little bit more on PSCAD study. As I mentioned, this is being used to assess stability in WinGrid areas, and this issues when you have a lot of inverter-based resources. PSCC may fail to identify instability issues, so this is where we use PSCAD. We also now cross-check PSCAD and PSCC models, and how how the responses from each tool can be compared, like if they're providing same response or similar response or not. We use PSCAD to identify this voltage, this weighted short circuit ratio, as I mentioned. Here you can see kind of with the growth of inverter-based resources in Panhandle, complexity of PSCAD model grew as well. So we needed to include more and more bigger and bigger area in the PSCAD model. And because more and more plant was being built, there needed to be more, CPU threads used for this model. Here you can see below this one example, the Panhandle area included in the study is more than 500 buses. It includes 60 PSCAD models for various inverter-based resource plants, and total capacity 10 gigawatt, and it takes 2.5 hours per contingency. I believe this is maybe a slightly older slide, and we were able to improve, but it's still like 1.5, close to 2 hours to simulate one contingency in PSCAD. So it's still very computationally intensive, and so we cannot do this study, say, in real time. I mean, ideally, that's what we would want to do, because then it would allow us to operate more flexibly and reduce containments, but we cannot do it right now. I think in the interest of time, I maybe go quickly through this slide. This is just talking about model quality test and model validation. As I mentioned, we require PSCC and PSCAD studies, models from plant owners. And so initially, once they were providing this model, sometimes they would not even initialize and would not work or produce consistent results across the tools. And so recently we developed a process for them to test models on their side. So it will give them a small test system where they could connect their model of their plant and do different tests. And they have to submit to us test report before we accept this model. And test report should show acceptable responses and that there is a consistency between PSCAD and PSCC models. And only after that, we'll take the model and we'll do our own verification, and then kind of plug it into the rest of the ERCOT grid model. So just in summary on WinGrid and stability, as inverter-based resources are being developed in the areas away from load centers and synchronous generators, we see increasing number of stability constraints because these are weak grid areas. We notice that simple metrics as a weighted short circuit ratio, they may not be applicable in areas where you have load and other synchronous generation. So it was very clean and clear for Panhandle until we got the city of Lubbock interconnecting. And we also noticed in South Texas that this weighted short circuit ratio could not be uniformly used in a similar way because the network is more meshed and it has more synchronous generation and load there. Synchronous condensers is a good help for weak grid areas, but it also introduces other challenges for a grid like Texas. There are limitations of available dynamic tools and models that can be, that we can encounter in weak grid conditions. Large electromagnetic transient models are time consuming, so we cannot do a big number of studies or cannot do it in real time. Modeling and model validation and keeping models up to date is ongoing issue. And we're also looking for voltage and reactive optimization tools that could dispatch closer in real time. And in absence of such tools, the operation may be suboptimal and too optimistic compared to real time conditions. So with that, I switched to inertia and frequency. I'll try to save maybe 15 minutes for questions. So I'll zoom through it maybe a little bit faster. So, you're probably all aware that the higher inertia you have, the lower rate of change of frequency it is after a trip of large generator. Did I say the lower? So the high inertia is the lower rate of change of frequency is, and the lower inertia is the higher rate of change of frequency is after a trip of generator. And so there is, if inertia is low, there is less time that's available before frequency falls too fast and reaches a trigger point for under frequency load shed. And so this time is time we have to arrest frequency and restore it back to 60 hertz. So this time needs to be taken into account when we implement measures for frequency control. So we kind of recognized that that's what's going on, that inverter-based resources are replacing synchronous generators. Inverter-based resources inherently don't have inertia. And so we started looking into that without seeing any issues on the grid. Actually, it was kind of preemptive from just what we've seen happening elsewhere. And so in 2016, we implemented real-time inertia calculation. We use inertia parameters of individual synchronous generators, and we use the on or offline status to calculate inertia for the entire system. We have telemetry from every generator with a lot of information that's in real time, and we get updated information every 4 seconds. So that provides accurate account of what inertia is there from generation. And of course, motor load also provides inertia contribution, but we cannot track it because we don't have real-time telemetry from it. And so what we do actually consider is when we do studies of how much inertia we need, we have load models there that, part of these load models are motor loads. And so with that, we do consider motor load in the models, because when we determine how much inertia we need, that inertia is only related to synchronous generators. But it's also, of course, not accurate, because in real time you may have more motors or less motors on than what we had in the model. So we do consider it, but it's not real time accurate. That's what I wanted to say. So this is how monitor looks like. So the blue line here is showing system inertia in real time. And then green line is showing forecasted inertia. So what we have from each generator every hour, they provide to us the current operating plans. And that current operating plan, it spans 168 hours ahead, and it has hourly resolution, and it tells us if a generator is planning to be online or offline, and a lot of other information. But what we use here is the intended status. And we use that status to calculate what inertia is going to be going forward. And of course, these plans, they are more accurate for the next maybe 24 hours, and then they're not very accurate, but we also don't need to forecast inertia that far ahead. And then, as I mentioned, they update those plans every hour, so we have an opportunity to update every hour. We also split by generation type, but we don't use this in operations. This is just for historic analysis, for trending analysis. We've calculated what our critical inertia is, and we define it as a minimum level of system inertia at or below which system cannot be operated reliably with frequency control practices that we have in place today. To calculate critical inertia, we simulate simultaneous trip of 2 largest units, and the criteria is that it shouldn't cause under frequency load shed. So we trip 2 largest units, which is about 2.8 gigawatt of generation, and the frequency should be arrested before it reaches under frequency load shedding level. And so we test decreasing inertia more and more in a test case. And once it hits the level where we go into under frequency load shed, then we bump it up a little bit, and that determines our critical inertia level. So right now it's set at 100 gigawatt seconds. We have visual alarms in the control room that will warn system operator once we start approaching that 100 gigawatt second level. What I think is also cool, we actually monitor what's the largest contingency is in real time. And so if two nuclear units, for example, are on maintenance, or one of those units is on maintenance, we'll switch to two next largest units, and we will also accordingly adjust critical inertia level to a lower value, because if it's lower size of contingency, then you need less inertia to arrest before under frequency load shed. So this is fairly interesting. This is our inertia trend. So if you remember the chart where I was showing how much inverter-based resource was installed on our system, you can imagine inertia probably declined drastically. But as you can see, from 2013 through 2020, it stayed. If you look at this box plots and look at this minimum inertia level, it stayed almost constant, actually increased in some years. And so it didn't decline with more and more inverter-based resources being added to the system. We did see close to 100 gigawatt seconds of inertia this year. And we are still kind of looking if this will repeat itself. We had a lot of wind in this March, and also a lot of plant on maintenance during this month of March, and so maybe that's what affected it. But it could be an outlier. We are not sure if we'll continue seeing this trend in the coming years. But this primarily due to several factors. As I mentioned, we retired quite a bit of coal generation. So here you can see in inertia terms retirements versus additions from 2013 through 2020. And you can see on the lower side of the chart, these are all retirements, and they are primarily coal and old gas steam units. And on the upper side of the chart, these are additions of installed capacity of inertia. And we installed a number of combined cycle units in 2014 and 2017. And just to mention, this combined cycle unit of the same size as coal unit has 1.5 times higher inertia. And this is because it has more rotating parts and more mass, and so provides higher inertia. So overall, this entire retirement and installation of new synchronous generators resulted in net increase of inertia in terms of installed inertia that we have. So it's not necessarily that all of this is online at any given time, but in terms of what we have installed, we actually added inertia to the system, and that is one of the explanations why the trend is not declining. I mentioned frequency response measures that are important, and the timing of these measures is important if you have if your inertia is lower and the size of your contingency is large. So what we previously had, a lot of frequency, about 50%, now it's 60% of frequency containment reserve was provided by load resources with under frequency relays. The second half was provided by generation resources with governor response or primary frequency response. We recently added fast frequency response service as well, and this is 1/4 second response time, full response, and sustained time is 15 minutes. And so this one is to address times when we have lower inertia, and this may help us to reduce amount of frequency containment reserve that we're carrying. You know, I'm kind of running short on time. I think I skip a couple of slides here. This basically is talking about method that we use to determine varying amounts of frequency containment reserves based on inertia. And so that resulted in, and this is an important chart here, I think, at different inertia conditions, we require different amount of frequency containment reserve. So this chart is showing if your frequency containment reserve all comes from governor type response, how much megawatt do we need at each inertia level. And this is all determined based on studies, and I have a method described in a few slides previously. And as I mentioned, we have this faster load resources that respond in a step kind of response within half a second of reaching 59.7 hertz frequency trigger. So this response is faster and it's more effective during low inertia times, and that's what we noticed. So what you can see here is equivalency ratio between 1 megawatt of load resource versus 1 megawatt of primary frequency response or governor type response from a synchronous generator. And so you can see here that as inertia becomes lower, this step and fast kind of response becomes more effective. And that allows us to decrease the total amount, reduce total amount of required reserve if we have participation of these load resources. So this is showing the kind of heat map based on expected inertia conditions, and then we are looking at history, 2 years history, how much reserve we need at any given time. So this is hours of the day, and this is months of the year. And so depending on expected inertia conditions during some periods, so you can see here in summer, we need very less frequency containment reserve. And this is because inertia is high and everything is online to serve load. But during shoulder seasons, as I mentioned, we have high wind, low load conditions, inertia is lower, and we need higher amounts of frequency containment reserve. This one is showing equivalency ratio. So again, equivalency ratio is 1-to-1 during high inertia conditions in summer, and load resources providing fast response, they're becoming more valuable during shoulder seasons when inertia is low. And I'll skip this and go straight to the summary. So from inertia and frequency containment reserve perspective, we observed that on average minimum inertia level was relatively constant in the past 7 years. Minimum inertia to date that we've seen is 109 gigawatt seconds, but prior it was 128 gigawatt seconds. It was all-time lowest. So we only just first time kind of got close to 100 gigawatt seconds this March. Right now, critical inertia is determined 100 gigawatt seconds. We do monitoring and forecasting of inertia in the control room, and the system operator has some measures in place to bring additional generation online with more inertia if it's needed. We determine our frequency containment reserves based on expected inertia conditions, and that allows us to operate more flexibly and procure more when we need more, and procure less when it's not needed. This fast frequency response ancillary services service was implemented in March 2020. Full response within quarter of a second to a frequency trigger of 59.85 hertz. And with implementation of this service, and once it's fully subscribed, we can actually reduce our critical inertia level, because now we have faster frequency response. And from the studies, we can see that we can go from 100 to 90 gigawatt seconds. We have, as I mentioned, we have 4 nuclear generators, and they are operating as a base load, so they are almost always online. Some of the ancillary services are being provided by synchronous generators, so they are also always online. And so because of this, we see that these factors, they bring about sufficient amount of inertia still, and it's kind of, we are not going to go much more below this 90 gigawatt seconds unless something here changes, unless nuclear units retire or synchronous generators stops providing ancillary services, and so there are these changes happening. And we also see more inverter-based resources seeking qualification for ancillary services, including wind and battery and solar. And so once they start providing services that were traditionally provided by synchronous generators, that may in turn affect inertia as well, because then synchronous generators have less reason to be online. And so, yeah, we'll keep monitoring this trend and we'll see what happens. I had a few more things to mention, but I think in interest of time, we'll just skip this. Maybe one interesting to stop here very quickly. This is a slide that I have.
I think we are doing fine with respect to time, Julia, so don't worry.
Okay. Yeah, so I think I'll still just kind of talk about this one and stop there. So this is a slide I put together talking about grid forming inverters and requirements for grid forming inverters. But this slide, I think it also fits for any requirement that is not yet commercially available. So there are, as I mentioned, you probably realize by now, as we introduce more and more inverter-based resources on the system needs are changing, and some services that we need are changing, and we would very much like inverter-based resources to be part of the solution and provide these services. But for us as a system operator, it becoming challenging to require things that are not commercially available. So like in the example with this power oscillation damping, this feature is not commercially available. So we get pushback from the market when we try to go out and require this. And I mean, rightfully so, they also have to go and procure it somewhere. And so what it leads to, in the absence of these services or these capabilities being provided by inverter-based resources, we say, okay, this is a stability constraint. We need to set a limit here. And so this leads to operational constraints that I was talking about in my presentation. As we said, this operational constraints, it becomes, first of all, it becomes more difficult to connect further inverter-based resources, and it also pushes them to areas that are less rich in resource because they're kind of trying to go outside of this stability constraints. So this results in shrinking markets for manufacturers because less inverter-based resources are being built. And then on the other hand, manufacturers are telling us, oh, you know, inverter-based resources can do much more. It's control. We can design different control features. So what do you need? And so this circle kind of closes because, because we cannot require what we need right away, but then manufacturer needs to know what we need to develop products that we need. And I've recently done a webinar looking at real cases, real life cases where grid forming inverters were installed. And one of the things I noticed is that these projects are very custom made. So each project is designed for a particular requirement in that specific area. So they say had some need for inertia. So there it is, grid forming project that provides inertia. And then in a different area, there is a need for to operate stably in WinGrid area. So there is a requirement for this grid forming inverter to do just that. And so there is no harmonization yet of what grid forming inverter is supposed to do or what it can do. And a lot of projects, I feel like they need to be tuned to certain certain grids and services that are required. So there is much more work to be done. It's good to see that there are pilot projects already happening, and then there are also some system operators around the world that started looking at what are functional specifications for grid forming. And so we currently in ERCOT we are not doing much proactively in our area, but we are looking out to learn from others' experiences and hopefully come out with either a service or interconnection requirements for inverter-based resources to support the grid and provide functionalities that we need for the system. So with that, I'm done. I have some references here for people in Europe. It won't be possible to download because our website is closed for people outside of the US. But if you're interested in certain reference, please email me and I'll be able to provide. Kashik, I didn't include my email in here, but maybe you can provide it to the participants.
Sure, I will do that.
All right. Thank you. Now I'm done.
Thank you very much for very, very detailed presentation and very, very important for the students here. And I see already there are many hands raising. We have from Water, who was our previous presenter. Water, please go ahead.
Yeah, thanks for the presentation. I have a question about curtailment. Is there a legally framework which allows you to curtail? What are the conditions and the tariffs, or is it specific for ERCOT?
I'm not sure how it is in other areas in US. I believe it's the same everywhere, but So we have this real-time economic dispatch and market, and so every wind and solar generator is on that market. And when curtailment is happening, I'm sorry, because of transmission constraint or because of over generation on the system, they are basically the only resource we can dispatch down. So overall in our market, we don't even call it curtailment, we call it economic dispatch. But yes, you're right, because they, I mean, they are losing potential power that they could have been provided. It is curtailment, but there is no compensation for it. It's just like on the market, when we look at the dispatch, they are the only ones that can be dispatched down.
Yeah, the only income in the Netherlands is the subsidy of the megawatt hour production.
Mm-hmm.
I'm not sure if that's also in the US.
So in the US, wind gets what's called production tax credit right now, and so when there is congestion and there is a lot of wind generation on the system, they offer in at negative price, and so that gives a signal to synchronous generators to come offline as much as they can, or operate at lower minimum generation level, but they have a set minimum generation level, synchronous generators, and they make a decision to stay online and still operate, and then this way they're paying to the market to still stay online while we are curtailing wind because we have extra generation on the system.
It's a little bit market mechanism that is used well.
Yes.
Okay, thanks.
Sure, thank you.
I also see Mustafa raising hand. Mustafa.
Yeah, thank you very much. Thank you, Kaushik, and also thank you, Julia, for this informative presentation. I saw one graph about the fast frequency response. I saw that the range was 1 per unit and the time window was 15 seconds. That 1 per unit is with regard to the power unbalance, or it's the capacity of the unit. Also, why is 15 seconds? 15 minutes.
So the response time is 1/4 of a second, and the sustain time is 15 minutes. 1 per unit, yes, it refers to whatever they offer. So if they sold, say, I don't know, 100 megawatt of fast frequency response, then we expect 100 megawatt within 1/4 of a second once frequency hits 59.85 hertz. 15 minutes, it's because we expect that in 15 minutes there are other mechanisms that should replace, because this fast frequency response is just to help us arrest frequency. And then after this, first of all, the primary frequency response will catch up, and then we'll have secondary response. We run AGC every 4 seconds, and so it will dispatch more generation to provide the secondary response and bring frequency back to 60. And then within 15 minutes, we would have run at least 3 real-time dispatch instances, so we can redispatch around and free up that fast frequency response capacity that's been used. Yes.
So this every few seconds you're checking with AGC every 4 seconds. That would maybe avoid the over frequency response. Is that true?
Yeah, it would take care of that too. And then another thing I actually failed to mention, because we are kind of island system, we require every generator on our system to be on primary frequency response. So what they have is it's 17 millihertz deadband, 5% droop setting. And so on synchronous generators, it's a governor response. On inverter-based resources, it's governor-like response. And so all generators on our system that are online will have this activated. We don't require to reserve capacity unless they are providing ancillary services. And so once, say, over frequency event happens, we have quite a bit of capability on our system for all generators to provide primary frequency response and regulate it down. And this is not paid for service. This is kind of like a reliability requirement for primary frequency response capability, and doesn't require reserving capacity.
All right. Thank you very much.
Sure.
Then we also have Damien. And I also have few questions, so we may go a little bit over time.
Hello, Julia. Thanks for offering to be here, and thanks for the early start as well. First of all, before I ask a few questions regarding your email address, I think if anybody wants to contact Julia, Julia was included in the Microsoft Teams invitation to this afternoon's event, so you'll find Julia's email address in there. A few quick questions. You mentioned at the start that the Panhandle had an additional 500 megawatts of load, and I wondered whether that was that good fortune that happened, or was that something that was planned and arranged? Given that.
Yeah, I'll maybe respond. You can continue after
Yep.
that. It's a good fortune that it happened. We overall have kind of lower. We have lower energy prices compared to that other area that city of Lubbock was connected to, and they also feel like they're part of Texas, and they want to be interconnected with the rest of the Texas system, and so they. I think the process was going on maybe for the past 4 years to interconnect, because I mean they were synchronous with the different systems, so it took a while to figure out. But overall, yeah, it helps to relieve this stability constraints on Panhandle. So it's just lucky coincidence.
Okay. And given that we're on this slide here that sort of shows the fast frequency response, I was wondering, and I know you sort of answered this, but given that you already have your primary frequency and your secondary frequency, and you redispatch every 4 seconds, I've sort of wondered whether the definition going from a quarter of a second or 15 minutes could be seen as an excluding certain technologies that could have given the fast response, but couldn't give the 15-minute response. And I suppose wind comes to mind here.
Yes. So there are several options here. So we also have this load resource. It's not limited to load. It's just a product, right? That currently only load provides. And here is response within half a second, but also step kind of response. But another thing that we did with this change of introduction of fast frequency response, some other changes happened to ancillary services. Another thing that we did, we said that regular governor type response from a synchronous generator, because we have 5% droop setting, in an event that will take us almost all the way down to under frequency load shed, they will be able to provide about 20% of the installed capacity as a primary frequency response because of 5% droop. But then, say, inverter-based resources like solar and maybe wind, if augmented with synthetic inertia functionality, it can provide faster frequency response, and it can do more aggressive droop. And so we said that with that, if a resource can lower the droop all the way down to even 1% droop, then they can provide up to 100% of ancillary service for this responsive reserve for frequency containment. All these 3 products, they are priced the same, and that was not how we initially designed it. We were like, our initial thought was that fast frequency response, or maybe it's more valuable, and the load resources are maybe more valuable during some times when inertia is low. But our market participants actually kind of insisted on having same price for all 3 products. So as I believe in here, inverter-based resources can find a way to participate if there is an interest.
Okay. Will Kaushik allow me one last question, or are we?
Yeah, go ahead.
The main question I was going to ask you was that you talked about the various stability analysis that you did and how you identified that you had problems. What I wondered was, how do you decide the next stage in terms of what are your corrective actions, and how do you select corrective actions that are, I suppose, minimum effort?
So for every maybe on never mind. For every stability, this generic transmission constraint that been defined, that's based on stability, we need to propose. I don't remember timelines, unfortunately, but we need to propose some exit plan. But exit plan to be approved, it needs to be either needed for reliability or it needs to be economic. And so curtailing or dispatching down generation is considered allowable action. So it may only show economic if, say, not curtailing, we can reduce overall energy costs on the system. And so any additional transmission needs to be justified this way. And so we periodically looking at each of these generic transmission constraints. They've been introduced at different times, so there'll be like a timing periodicity with which we look at those, and we reevaluate different solutions. So we run studies, reevaluate different solutions, and once we find a solution that's economic or absolutely needed for reliability, then it's been implemented. And then also as a part of some planning studies, we also evaluate kind of broader spectrum of transmission solutions that may relieve some of these generic transmission constraints as well. Okay. I hope this answers the question.
Yes, thanks very much.
Thank you, Damien. Then I'll ask a couple of questions myself. I was wondering, while you were presenting, I also checked the wind atlas and solar atlas. Both Texas is blessed with both windy and high sun. So what do you have view on hybrid power plants of wind and solar to accommodate in your system, because they increase the flexibility as well as service provision and may also reduce your curtailment through more economic dispatch?
Yeah, so one thing to mention maybe, it's in Texas Panhandle, the capacity factors that you can see are comparable to offshore. So you can see even up to like 50% capacity factor on wind in Panhandle. So it's very wind rich. And to your question, sorry, I forgot what the question was.
The value of hybrid power plant.
Value of hybrid power plant. Yeah, so we are not seeing much of, it's all market driven, right? We cannot recommend any type of plant being built. So it's whatever comes our way. Right now, we're seeing more hybrids, battery and solar type of hybrids. And this is primarily driven by incentives. So I mentioned we have investment tax credit for solar, so that 30% of the investment can be retrieved through tax credit. And so now this tax credit has been, this incentive has been broadened to include storage that's co-located with solar. And there are some constraints about how they are supposed to operate, but it's just federal incentive that provides this interest for co-locating solar and storage. If it's helping, I'm not sure if it's when they're developing, they have in mind how it may help the system, because like if you think about it, solar right now is building here because of solar resource. And yeah, they are placing battery nearby as well. Some of the transmission constraints may also hit that battery. So I mean, it may save some solar during daytime, but yeah, but it's also inverter-based resource in weak grid area. And so it may be also constrained from that perspective. So I guess for wind and solar, we are not seeing any projects at all for co-location. We've seen a couple of projects, wind and battery as well. And that should be driven just by pure economics. So they are probably considering to save curtailed wind, store curtailed wind, and use it later when there is no congestion on the system. And we saw another interesting thing. We saw batteries being co-located with gas turbines in some instances. So there are actually more projects where batteries co-located with gas turbine than battery co-located with wind right now in the interconnection queue. And what they want to do with this is going back to ancillary services. Some of the ancillary services are required from generators from online state. But if they co-locate with battery, the battery can start providing service, and then the gas turbine will start. So that allows them to turn gas turbine off and still sell ancillary service that's required from online resource on that one. So that's kind of interesting thing that we see.
Yeah, that's very interesting. Yeah, because both of them try to provide very fast services, and then it's like one way of hybridizing the storage itself in that sense. But yeah,
right. But then that also provides them opportunity to say provide PFR, because battery can start providing PFR, and then gas turbine will come on. And then for PFR, sustain time is up to an hour. If we are, I mean, we've never been in frequency event for an hour, but theoretically it can be required to stay on for an hour.
Right, exactly. But then I will ask one more question, and I will presume Anka will forgive me for that. take her time. But the inertia, real-time inertia calculation, do you do it at, so it's a two-part question, do you do it at complete system level at for whole Texas, or you also divide it locally within the Texas? And then the second part, do you see any other, except for monitoring whether it's close to critical inertia, do you have any other application of real-time inertia calculation?
First was, if it's system wide, we calculate for the entire system. We looked into, I've seen some works in other systems, for like local inertia stuff. We looked at our frequency. So say we had this February freeze event, and during this event, quite a bit of generation tripped, and so we had a deep frequency event. And during this event, we looked at the system, and the frequency is almost, if you look at PMUs, 50 PMUs across the system, the frequency is almost the same all across. So we don't see a lot of variation in frequency right now. And that's maybe, it's maybe because most of synchronous generation is still kind of concentrated in the central part of Texas, and this is it. I'm not sure why it doesn't vary across our system as much as in some other areas, but based on that conclusion, we decided it makes sense to just monitor inertia system wide for now. And then second question you had, if we are using monitoring for anything else. So we, as I mentioned, this frequency containment reserve is based on expected inertia conditions. So in the day ahead, we procure amount that we think we need, and then we monitor sufficiency in real time. And so we monitor what inertia is right now and what inertia is forecasted to be in the next few hours. How much frequency containment reserve do we need at these inertia conditions? And then have we procured enough? And if we haven't procured enough, then we are looking at all other available frequency responsive capability. So if there are plants that are not operating at the full capacity, they are still frequency responsive, right? Because I mentioned we require all of them to be frequency responsive. So we'll use that kind of free capacity, and we will not procure more of responsive reserve. But if there is nothing else available, then we can reopen ancillary services market and procure some more.
Great, thanks a lot. I think that was very nice presentation and very nice discussion we had. Thank you again for joining very early, like Damien said. So thank you, Julia.
Thank you. Thanks for all good questions, and Anka, sorry about time.
No problem. No problem. It's a pleasure to